So now we're finally ready to derive our mathematical model for our one-dimensional kinematic situation. So the way we're going to do this is we're going to start by making some simple graphs of different objects moving around in one dimension. Um, and from that, we're going to need to use our algebra skills to try and derive some formulas from those graphs. So what I mean by this, let's just start with a very simple example. We've kind of got all of our terminology down. We kind of know a little bit about how position, velocity, and acceleration are related. We're going to start graphing those things, and we're going to see what we can come up with. So the simplest situation we can think of, let's just have a person walking across a room. Let's see what we can graph from that. So what we're going to do, we're going to make graphs of this person's position as a function of time, their velocity as a function of time, and eventually we'll also get to their acceleration as a function of time. So here's what our position versus time graph is going to look like for someone who is just simply walking across the room very slowly, right? Um, so again, what I'm doing here is I'm going to graph their position on the vertical axis. I'm going to graph time on the horizontal axis. You're probably used to seeing x over here and y over here. I'm flipping that around. If you remember right, this is a two-dimensional graph, but we only have one spatial dimension that we're working with, right? We just have the one direction that we can walk. We can walk forward and backward in this room that we're standing. But of course, as we're doing this, some time is going to pass. So let's say we'll put the side of the room that we start on as our um, as the origin, right? We'll say that that is where our position is 0. We're right at the center of our coordinate system there. So if I start there, if I start at the origin and then I walk across the room some distance and I do so at a constant rate, what this graph will then look like is something like this, right? We just have this nice straight diagonal line where over time, as we walk across the room, our position, right, our distance from the origin point is increasing, and of course, time is also increasing. We're not super worried yet just about exactly how fast we're going or how long this is going to take us, but for just someone moving across the room in one direction at a constant velocity, what we end up with is a graph that looks like this. Excuse me, if we think back to what we know from algebra then, what does the formula that describes this line look like? What we end up with is something like this. We have x equals x naught plus v times t. So this is describing, this is essentially I've already derived a formula for our position as a function of time given some speed, right? So again, this formula here that we have here is very analogous to our very simple straight line formula, y equals mx plus b. Of course, we're not using x and y, we're using t and x in this case, right? We have time and we have position. And in this case, what I'm saying is our position as a function of time, right? Our position here as a function of time is wherever we started out, right, at the beginning, whenever time was 0, this is what our position was. In this case, it was 0, right? But I'll still include it for this case. Plus our slope times our time. Why do I have the slope written as v in this case? Well, the slope of this line here is actually going to correspond to how fast we're going, right? The steeper the slope, the more quickly we are covering this ground. The shallower the slope, the slower we are moving as we go across this room. So this slope here will actually end up corresponding to our velocity. There's a couple different ways that we can show that as well. So this is my position as a function of time graph. What happens if I make a velocity as a function of time graph for this same situation? Oops, this should be t, not 4. There we go. So yeah, so if I have velocity as a function of time, in this case, what do I end up with? What does my velocity as a function of time look like for someone moving at a constant speed over the course of this trip? It will just simply look like this, just a nice straight horizontal line, right? We start out with some speed, we maintain that whole speed, we maintain that velocity throughout the entire course of this trip, right? So of course this formula for this one is a little bit simpler, right? There's just a straight horizontal line. We don't really have anything interesting here. It would just simply be this. We'd just say v equals v. This doesn't really help us. We'll kind of come back to this here in a second. But for now, let's look at this again. Let's look at this graph. Another way I can write this is like this. I can say x, I can just subtract the initial position off of both sides, minus x naught equals v times t, and this of course is my position minus my initial position, which is also known as my displacement. So you can actually also write this formula in terms of the displacement, right? So this is writing the formula in terms of position as a function of time. This is kind of my displacement as a function of time, right? These delta x equals v times t, right? So yeah, so with this, we can say this is just a nice simple formula. If you're moving in a constant straight line, what you end up with is delta x equals v times t, or again, you can say displacement equals speed times time. You also have probably heard the formula before, distance equals rate times time. This is essentially what we're doing right here, right? Our rate in this case is just our v, just how fast we are moving, right? So let's take a look at this again, though. Let's go back. Let's revisit this graph here. So what information can this graph tell us? At first, it doesn't seem like it's very useful, right? We just have some sort of constant v. We just have this straight line thing happening here. And so we don't get this very interesting formula, right? I have v equals v. It's just whatever the initial speed is the speed for all time. However, there's one other thing that we can actually, one other piece of information that we can derive from this graph. And it's not obvious at first. If you've taken calculus, it might be. However, again, we're not going to do any calculus, so this is about as tricky as it gets with regard to that. So you're just going to have to take my word for it if you haven't taken calculus. Let's go ahead and let's calculate the area underneath this velocity graph, right? So what do I mean by that? So if we can say we have v versus t right here, right? We have some sort of constant speed for some amount of time. If I calculate this area of this graph, it's not actually an area, as we'll see. What does this correspond to, right? We have a v, we have a t. How do I calculate the area of this rectangle here? It's just going to be v times t, right? So if I calculate the area, I get v times t, right? So this distance here is v, this distance here is t. What does that give me? What is v times t? Well, if I look over here, v times t actually is my delta x. So we can actually get back to this same formula from this graph of velocity versus time as well. We have to do this weird thing, this kind of awkward thing. Again, this is where if you haven't taken calculus, I'm kind of tricking you into doing calculus right now. If you have taken calculus, you know exactly what's happening. This is as complicated as it's going to get for the calculus as far as we're concerned. Everything else is just algebra. When I calculate this area under this v versus t curve, what I get is this. I have v times t, in this case it's a nice simple rectangle, and what we end up with is v times t does correspond to the displacement, right? The actual displacement that took place for this trip. So when we have the position versus time graph, it's very easy to see, right? We're just graphing position. Of course, then you can just find displacement very simply from that, very intuitively. When you have the velocity versus time graph, however, there's this kind of awkward, unintuitive thing. Why would I calculate this area? I mean, the area itself is easy enough to calculate, right? It's v times t. Why did I do that? Who knows? If you want to find out, again, take calculus. But for now, we just need to take our word. You just need to take my word for it. If you do this, if you calculate this area underneath this curve, what you will get is you will get back to the displacement of your object for that trip, right? So right now, we've already kind of gotten back to some of these formulas. We've already used these before when we were talking about, you can rearrange these. You can say v is equal to what? You can say v is equal to delta x over t, which of course, t you can say is the change in time. If you want to call that delta t, that's fine as well. This is kind of what we've been dealing with before with our definitions of v. And you can very simply see that this also does, in fact, correspond to the slope. We have v equals delta x over t. This is your rise over your run, right? So this does correspond to your m, and the y equals mx plus b. V is, in fact, the slope of your position graph, right? And that should make sense. If the definition of velocity is the rate of change of your position, right? When we're talking about this in mathematical terms, the slope of our graph is how quickly the values on our graph are changing, right? So v should be this slope. So this is a nice simple case here. We just have this constant straight line velocity occurring. We're just moving in a straight line at a constant velocity. This is pretty much everything we need to describe that situation. So let's make it a little bit more complicated now. Let's add some acceleration into this and see how that changes it. So we're still doing one-dimensional kinematics, but we're kind of making these situations a little bit more and more complicated as we go every time. So now we're still going to do these position, velocity, and we're going to throw some acceleration graphs in there as a function of time. We're going to make the situations slightly more complicated. So this time, instead of just a person walking across the room at a constant velocity. Let's graph the situation for someone is sitting at a stoplight. You're in your car, and the light turns green, and you hit the gas, and you start to speed up as you move. So in that case, what does my position as a function of time graph look like? So it's going to look like, and I'll explain this here in a second, is going to look something like this. This is what my position as a function of time will look like. We have this now, we have this kind of curved line, um, increasing slope that we have as time increases, as we can continue to accelerate. Why is this? Well, as we said before, the slope of this graph here, the slope of my position versus time graph, has to correspond to my velocity. What does my velocity start out with? It starts out at 0, right? As soon as that light turns green, I am not moving yet. I've hit the accelerator, right? But our velocity for that instant is still going to be 0. However, as time increases, my velocity increases, which means on this graph, the slope itself must also increase, right? We have to get steeper and steeper and steeper as this goes, as we speed up. And so from this, you can see, right, as time increases, the slope increases, we start to move faster and faster, we start to cover more distance as a function of time. So this is my position versus time graph. We have this nice curved parabolic graph that we have here. What does my v as a function of t look like, right? So in this case, we have v and t again, but now our v is what's increasing, right? We have my velocity, again, we said starts at 0, and it increases with time, right? We are accelerating. So now my velocity graph does have some sort of slope to it. So essentially what we're trying to get back to is we're trying to get to a graph of this, right? We want to get to this position as a function of time with acceleration. We already did that with our other one, right? We had just our delta x equals vt for the situation with no acceleration. Now let's say we add in some acceleration, but we're also going to have still our initial velocity be 0, and that's what this case looks like here, right? So we have our slope is increasing, which means our v, graph of our v versus t is now just this constant straight line as our v is increasing as a function of time, right? And then what does my acceleration as a function of time graph look like? It's going to look something like this, right? So now we have this straight constant line where acceleration is going to be just some sort of constant value as we speed up, as we move through this intersection here. So we have these three graphs here. So what information now can we learn from these graphs? So before, with a nice simple situation, no acceleration, we had our position as a function of time. We just had this nice straight line, and we could very easily read off. We knew y equals mx plus b. You can kind of do that for this one if you remember the formula for it, but I think it's going to be more useful to use this type of stuff here. So now what do we have? Let's start writing our graph for v as a function of time. Well, we can still do our y equals mx plus b because we do have this straight line graph here. However, since it's the velocity, we need to make sure we specify that. We're not talking about positions. We have v equals v naught plus a times t. So now this is again analogous to my y equals mx plus b. However, my slope in this case is my a, and this should make sense, right? Our velocity is analogous to our position as our acceleration is to our velocity. So the slope of my x is my v, the slope of my v is my a, right? So this a is now my slope, right? This time is still my independent variable here. So we have, we can also, of course, rewrite this. We can do it the same way as before. We have v minus v naught equals at. We can get delta v equals at, right? So this is good. This is useful. We definitely want to have what our velocity as a function of time is in this case, right? It's our initial velocity plus whatever our acceleration times our time is, right? So if I started at 0 miles per hour and I accelerate at 5 miles per hour per second per unit time, 1 second has passed. 0 plus 5 times 1 is 5. After 1 second, I will be moving at 5 miles per hour, right? So yeah, so again, this is going to work exactly analogous to the way our position as a function of time graph worked previously in the case with no acceleration. However, we still want to get back to this position graph, right? Which we don't have a formula for that just yet. So how are we going to go about doing this? Well, we can actually do it the same way that we did before. If you remember what that is, we're going to again need to calculate the area underneath our velocity as a function of time curve. What is that area? In this case now, what we have is, instead of a rectangle, we have this triangle, right? So this height is v, this length here is t, and if we do half of v, right? If we do 1/2 of v times t, let's look at this area here. One half of v times t will give us the area of this, right? So in this case, this is what's going to be equal to our delta x. Delta x equals 1/2 v times t, right? And so this again should make sense, right? Now we have some sort of acceleration happening. So it's not our final velocity times our time, which gives us our final position, or our displacement in this case. It is going to be half of our final velocity times our time. Why would it be half? Well, half of our final velocity is actually our average velocity, right? We spent some time traveling 0, we spent some time traveling at a speed v, but on average, our average velocity was half of our final velocity. And this is going to work for this case where, again, we started at this 0 velocity. So we can, in this case, we can say x equals 1/2 v times t, right? However, how else can we write this v? What else can we write v as? We know that v is also going to be what? This v, this is our final velocity, right? Is going to be, in this case, a times t, right? So there's a couple different ways that we can write this. We can also say that delta x equals 1/2 a times t, which will be t squared. So this is another way that we can write it, right? In this case, we can say, for the case where we have a 0 initial velocity and then some sort of constant acceleration after that, we can say delta x equals 1/2 vt, or delta x equals 1/2 a times t squared. And this will give us our position as a function of time for some sort of acceleration that is occurring, some sort of constant acceleration that we have. So again, of course, here we can just say a equals a. There's nothing tricky about this one. So this is a good time to point out, for our purposes, we are only ever going to be dealing with constant acceleration, right? So whenever we do these graphs like this, if we're ever gonna try and figure out what's going on, we will only ever have this constant acceleration. So this is all we have to worry about. There is one other thing that we can do, though, to make these situations slightly more complicated. It's not changing the acceleration, but there's one extra thing, one extra wrinkle that we can throw in to try and find our most general formula for our position as a function of time. And what might that be? So again, we're still on 1D kinematics, and we're going to come up with the most general formula that we can now for our position as a function of time, assuming that we have constant acceleration. So what's one more situation that we can come up with? So far, we've had someone walking across a room at a constant speed. Then we've had someone accelerating from a stoplight with an initial velocity of 0. And now the last thing that we're going to do is we're going to say, we're going to start with some initial speed, some initial velocity, and then from there, we are going to accelerate even faster, right? And that's kind of the most general case that we can work with. We don't know what the initial speed is. We don't necessarily know what the acceleration is, but just in general, we can say, let's start with some initial speed and then speed up from there. So what situation might that look like? Again, if you're just driving along in your car and say you're leaving a residential area, getting on the highway or something, you're traveling along in a straight line and the speed limit increases from, say, 30 miles an hour to 60 miles an hour. You're going to be moving along. You already have some sort of initial speed, right? So initially, what's the slope of this got to be? It's got to be something positive, and then it's got to increase from there, right? So we start out with some initial speed and then we increase our speed after that, right? So again, just driving along your car, speed limit increases might be some sort of physical situation you could think of where this would happen. So now we have this, we've started with an initial speed and our speed is also increasing. So again, it's pretty tricky to just read off from that graph what our position as a function of time is going to be, but by now we've had some practice at this. Let's go ahead, let's make this v versus t graph, and we can go ahead, we can fill in our a versus t graph as well. This will be nice and simple. We know it's going to be something constant. I'm telling you that right away. Our a is always going to be constant for our purposes, right? So yes, we have our position as a function of time. We have our velocity as a function of time. What does our velocity as a function of time look like in this case? Now what we're going to say is going to look something like this. We don't start out at 0. We do start out with some initial velocity, and then our velocity increases from there. So now what kinds of formulas can we write from this one? We can still say this formula is going to be correct for our v. We can say that v is equal to v naught plus a times t. In this case, we now just have a non-zero initial velocity, but of course I can still rearrange it if I want to. I can still say the same thing that we had before, say delta v equals at. This will always be true, right? The change in velocity is equal to your acceleration times your time, right? Your acceleration is your rate of change of velocity, so multiply that by however long you're accelerating, and that will give you the amount that your velocity has changed by, right? But yeah, so we still need to get back to this position as a function of time graph. So what's the way that we've done it now? What's the way that we've been doing it forever? Let's go ahead and let's calculate the area underneath this curve. Now we need to have this triangle and we have this rectangle that we're going to need to take into account. So we'll calculate both of those and we'll add them together and we will see what we get for that area, which we know will also correspond to our delta x. So let's calculate this area. We have this triangle here, which is going to be what? We have this is going to be about the halfway point. So this is V, this is V initial. And what we can say is we have something that looks like this. If we want to calculate this area, I would say the area is equal to what? V naught times T plus what? Plus the area of this rectangle. What is the area of this rectangle? It's going to be, sorry, the area of the triangle. I already did the rectangle. The area of the triangle is going to be 1/2 of the difference between V minus V naught times T. So now this is kind of a big complicated mess that we seem to have here, right? But we can, sure enough, get back to what we want. We can get to a nice simple formula here. And so the way we need to do that is we need to recognize that this 1/2 V minus V naught, we can rewrite this. How do we write that? It's going to look something like this. So this term stays the same, plus 1/2. What is V minus V naught? What is this here? This difference in our final velocity minus our initial velocity. This is just our delta V, right? So with this, we then have V naught T plus 1/2 delta V times T. But how else can we rewrite delta V? We know that delta V has to be A times T, right? We still have this up here. And so we end up with our final formula looking something like this. And this is going to be our area underneath this curve. The area equals V naught T plus 1/2 of the change in velocity times time. The change in velocity we know is A times T. So we have delta V times T is A times T times T. So of course we have this should look familiar from what we had before. And what we end up with is this. We have V naught T plus 1/2 AT squared for our delta X equation. And so that will do it. So that will be our most complicated formula that we're going to use for position as a function of time. If you wanted to at this point, you could go through, you could keep doing this process over and over and over again. You could add more terms on. You could get like a t cubed term if you wanted. And you could do that by saying, okay, let's see if we have some increasing acceleration, some sort of non-constant acceleration. You have to come up with a term for what does your change in acceleration mean. And so on and so forth. You can do this as far as you want, but for now, for our purposes, this is going to be where we end at. We're going to say, okay, our acceleration is always constant, and if that's the case, if we're only ever dealing with constant acceleration, the most complicated situation we can come up with is we already have some sort of initial velocity, and we're going to accelerate up from there. And if that is the situation that I have, we can now very precisely calculate our displacement. We can calculate our change in position from wherever we started by saying it's v naught t, our initial velocity times our time, plus 1/2 a t squared, right? So that'll do it for now. The next thing we'll do is we'll start looking at some examples of how exactly we're going to apply these to a couple different physical situations.